You have a series circuit, and you have letters that are placed all around this circuit. And your task is to look at this and say, well, I also have 3 voltage sources. Do I have series aiding situation? Do I have a series opposing situation? How do I deal with this? We played with this one several times before with series aiding and series opposing. Do these sources move current in a similar direction? If they all move in the same direction, then they're series aiding. If 1 or 2 of these are not moving things in the same direction, then something is canceling something else. All right? And how do we play with something like this? You'll figure that out. Voltages at specific points to ground, from A to ground, B to ground, C to ground, and then also between different points. 21 points for that exercise. O-scope reading and triangle sides. I don't have a SOHCAHTOA thing in here. Then you have a series reduction. You have a series parallel reduction. You have this guy. What do you do with this? You are asked to redraw this at least twice for the purposes of simplifying it. So the first redraw that you're going to do is going to be what? What's the first thing that we do when you see something like this? Think about that, okay? So what we'll do is these are things for you to think about. I've gone past my time. I won't take up any more of your time, but I will stick around for anybody who would like to have some helpful hints on how to approach this. So let me go ahead and do this. Everybody show me your smiling, friendly faces so I can take a picture for the dean. And I will excuse those of you who choose not to stay. You're not required to stay. Let me get off of the share and come to, come on, mouse, be nice to me. And go to camera. Cool, I can see me too, yay. And then do the grid. I can see everybody. All right, okay. Okay, so here, and oops, too much zoom. And let's see, Ephraim, you don't have a camera. Javier, you don't have a camera. Okay, 1, 2, 3, and smile. Yay. Okay, got the picture. All right, so now I know who's here in attendance. Class is officially dismissed. I am going to stick around for whoever would like to stick around, and I'll give you some helpful hints on how to play with this practice test. So class is officially over. Adios, have a lovely weekend.
Thanks, Mr. Teacher.
My pleasure.
Thanks, Professor.
My pleasure. Have a lovely weekend. Okay. All right. I will talk about how to play with some of these exercises and not so hard to think about it. Very quickly, a good solution for you would be this. Let me go to share. Let's go to this, do this camera and speaker view. All right. So if I were to show you a voltage source and a resistor and another voltage source and a resistor and one more voltage source, or one more resistor and one more voltage source. And I were to say that this one is equal to 7 volts, this one's equal to 3 volts, and this one's equal to 12 volts. And I'm going to say this is equal to 100 ohms. And I'm going to say this is equal to 200 ohms. This is going to be equal to 300 ohms. This will be R1. This will be R2. This will be R3. This will be point A. Right here will be a point B. Right here will be a point C. This will be a point D. This is a point E. And this is a point F. Copy the thing first. Be very mindful how you copy the plates. So as you're copying, what we're going to need here, my friends, is we're going to need a VIR table. For R1, R2, R3, and totals. And you can fill in what it is that you're given. What it is that you're given, R1 is 100 ohms. So fill that in. R2 is 200 ohms. R3 is 300 ohms. Right there. And is this a parallel circuit? Is this a series circuit? Is this a series parallel circuit? How do we name this circuit? How do we identify this circuit? Question goes to Tony. What do you think?
Series?
Series. Okay, Jess, why is this a series circuit? Do you agree with your classmate? You have a different opinion?
I believe that's a series circuit because the resistors are in series.
The definition for a series circuit, you're both right. Series circuit is identified as having one current path. That's your definition for series. As long as you have a singular current path, this is series, okay? So even though the resistors aren't touching each other, they are all interconnected in one loop. The loop has no other branches, just one loop. It is a series circuit, one current path. So that's your definition. So if they are in series, can I easily determine my total resistance if I know that they are in series? Because what's my RT in a series circuit? How do I determine my R total? Javier?
You add them.
You add them. And if you go to add these guys up, Javier, what's this add up to be?
500.
I beg your pardon?
500.
500? How many people agree with 500? Did you use your calculator for that?
600.
Are you sure now? Okay, yes. Here's where you have to be really careful, especially on a test, because watch this. If we wrote down 500 and we weren't paying attention, would all the rest of this be wrong? Big time. We would be crying the big tear, okay? So your first calculation, you should always double check and make sure you have the confidence that it is what you think it is. And if you believe it's going to be 600, then so be it. It'll be 600. What else is given? Pardon me. Your voltages are given. You have a 12, you have a 7, and a 3. But you need to reconcile total. So how do I reconcile total in this particular circuit? So we have to determine in which direction these voltage sources move electrons. So the very first thing you're going to do, the very first thing you're going to do on the schematic is you're going to mark your polarities. Negative here, positive here on that source. Negative here, positive here on this source. Yes? Negative here and positive here on this source. Are we okay with the marking of the polarities in red? Next, what you need to do is you need to determine the direction of how each of these moves electrons. How does the 7-volt source move electrons? It moves it from the negative plate. So if it moves it from the negative plate through the circuit this way, what do we call the direction through the 7-volt source? From the 7-volt source, what do we call this direction of electrons?
Counterclockwise.
This would be called counterclockwise. So this is a CCW, yes? Now take a look at the 12-volt source. The 12-volt source has the electrons here. So it leaves this plate. What do we call the direction from the 12-volt source?
Clockwise.
Clockwise.
Exactly, clockwise. So that's a CW. Finally, let's look at the 3-volt source. So the 3-volt source has the electrons leaving the top plate, so it moves in this direction. What do we call this direction from the 3-volt source?
Counterclockwise.
Counterclockwise. Counterclockwise. So you do a clockwise and a counterclockwise T-table, and you just fill in the numbers. So counterclockwise, you have 7 volts. Counterclockwise, you have 3 volts. Clockwise, you have 12 volts. So what's these two add up to? You've got 10 volts over this side. What's this add up to? 12 volts over this side. Which one's going to win? Which one is dominant? Which one of these numbers is bigger?
12 volts.
12 volts is bigger. This is bigger. So if this is bigger, then this is what determines your final direction of electrons flowing through the circuit. Okay? The final direction is determined by whichever side has the larger total. In this case, the larger total happens to be on the clockwise side, this one here. So the direction of electrons is not determined by this guy, not determined by this guy, but finally by this. So if we go to fill in our directions of electrons, electrons will flow here up and flow here and flow here and down through this resistor here, through this resistor and back to here. Is everybody in agreement with the direction of the arrows in this drawing? So far, so good? Now,
Yes.
now you have to mark the polarities of the voltages, of the polarities of the resistors. So when you go to mark the polarities of the resistors, my friends, this is what you're going to get. The polarity of R1, the electrons flow from this left side to the right side. That makes this side here negative, makes this side here positive. That's critical for us to know that. The electrons flow from the top to the bottom of R2. It always enters the negative side of the resistor and exits the positive side of the resistor. The electrons flow from the right to the left through R3. That means this side is negative, this side is going to be positive. Are we okay with how the polarities of the resistors are marked? The polarities of the resistors are determined by the direction of our final current. And our final current is moving, in this case, from the negative side to the right positive side of R1, from the negative side top to the bottom of R2, from the negative side right to the positive side of R3. Are we okay with these polarities so far? Okay. Now, do I have a net voltage? What is 12 take away 10? 2 volts. That's my total source voltage right there, my friends. The 3 voltage sources, the 7, the 3, and the 12, all work out to be a net of 2 volts. That 2 volts is pushing electrons in this direction. Okay? Is everybody okay with this number here?
Yes.
The rest is academic. All of this is completely brain simple, okay? Because Ohm's law says as long as you have 2 quantities, you can calculate that missing quantity, right? So are we confident that the total is 600 and not 500? Are we confident that the voltage is 2 volts and not any one of the singular values up here? If you're confident in these 2 numbers, can you calculate a current with confidence? Go ahead and do that, please. So 2, turn on calculator code, 2 divide by 6, clear. 2 divide by 600, and engineering. So the question for current works out to be what value? Ephraim, what do you get for current, my friend?
Calculating right now. 1 second, please.
2 divide by 600.
It's let's see, 30. No, 1, 2, 3, 3.33 milliamps.
3.33 milliamps. How many
Yeah.
people concur? So far, so good. Now, since this is a critical calculation, could we take a moment and do it again? Sure. 2 divided by 600. Only takes a second to do it again. Engineering, hey, it is 3.33. Now you have the confidence. Well, guess what? This was a series circuit because it only has one current path. You have found a current that you calculated twice. You're really confident with this because this is a series circuit. Now can we fill in this column? Do we have the confidence to fill in this column of currents? The answer hopefully is yes. 3.33 milliamps. So are we good with that? So far, so good. Hey, boo-boo. All right, now we want to calculate voltages. Voltages is I times R. So this current times this ohms. So this times 100 will give us 333.33 millivolts times 2. This will give us 666.67 millivolts. And this will give us 1 volt. Are we okay with these calculations? So far, so good. Haven't worked any magic with you yet. The magic's going to happen in a moment. All right. So now you are asked. Well, I have to put a ground here somewhere.
Professor, I have a question.
Yes.
If the 7 volts and the 3, well, if all the volts were the other way around, so whatever they have right now currently is the other way around, would it be negative 2 volts?
Nope. Nope, it's a net 2 volts. Because the potential, the potential of the sources as sources, solely as sources, is simply a magnitude. So this has the potential of 12 volts, whether it's positive or negative depends on how we hook up our leads. So
Got it. Thank you.
if all of these were flipped around, we would not have a negative 2 volts. We would still have a 2 volts as being the net potential to move these electrons around in this circuit. So that being said, now what you're asked for is voltage. I have to put a ground here. Okay, I'm going to arbitrarily throw a ground right here. That's my ground. I'm going to put it up here. Everybody see where I put the ground? And what I'm going to do is I'm going to write the values of these voltages in my schematic. So could I do this? Could I make this just for now, make this a 0.33 V? Is that all right? 333.33 millivolts. It works out to be like a 0.33. And across here, I have a 0.67, just for easy math. It's 666.67 millivolts, basically 0.67 volts. And the voltage across this guy is 1 volt. Okay, just to keep the math simple. Now, what you are asked for is voltage at point A, voltage at point B. So what is the voltage at point? Let's take these 3. If you're asked for the voltage at point A, my friends, aren't you going to take the red probe of your multimeter and you're going to put it on A? Where is the black probe going to go? The black probe is going to go to ground. Well, where is ground? Ground is also at point A. Wow. If these 2 probes are touching the same point, is there anything between these 2 probes other than the ink on my paper? Nope. How much voltage do you anticipate to be here at point A? 0 volts. Nothing there. How about at point B? Now point B becomes more interesting. You have to take the probe and now move it to point B. So physically, this is now at point B. and the black probe stays at ground because this is our ground right here. Is there potential between these 2 points? The answer is yes. Is there a polarity that the red probe sees first as it's being pulled towards the black probe? See, right here, the probe sees the negative side of the 7 volts, and it also sees the positive side of the 0.33 volts. Which polarity is it going to read? It will read the polarity that it first sees as it's being drawn towards the black probe, which will be what polarity, my friends?
Negative.
Positive. The red probe sees the positive of the R1 resistor. Does everybody see what I'm talking about? It
Yes.
sees both the negative of this source, and it also sees the positive of this resistor. Which one of these will it read? It won't be looking at that voltage source. It'll be looking at solely what's between these two. And the very first thing it sees as you pull it towards the black probe, it sees positive.
Does it see the positive only because of where the black probe is placed, or because
yes,
of the current flow?
No, the current flow determines the polarity. The direction of current flow was from the left to the right, and the direction of that current says this side of the resistor will be negative, this side of the resistor will be positive. And as we put the black probe at ground, which is point A, and I put my red probe here, what the red probe sees as is being pulled towards the black probe is a positive 0.33 volts, or positive 333.33 millivolts. Okay, that's what we'll actually write down on paper.
What would happen if you were to switch the two?
Then it would be negative. If I switch these two here, because remember the red probe is being pulled towards the black probe, the first thing it sees will be a negative 333.33 millivolts. That's what will happen if I switch to 2. Okay,
and
Jeff?
would it matter if you put the ground at point B?
Well, yes, I would. I'm totally changing the ground point then. Let's continue with this because you'll see what happens. I'm just going to leave this at point A, and the rest of the circuit will be referenced to point A. Let's go on to point C. At point C, here's the red probe at point C. The red probe at point C, and the black probe here. What is red between these two probes? Well, the very first thing the red probe sees as we move it in this direction is what polarity? Positive. What value? 7. So we have a plus 7 volts, and we're going to add that to, what's the next thing that we see? Will be a positive 0.33 plus 0.33. So what does my point C calculate to be? This calculates to be a positive 7.33 volts. Are we okay with that from C to ground? Next, we will go to D. So here is point D. So who would like to venture to guess what my voltage is going to be at point D with respect to ground? The voltage at D. At point D, again, you just pull it in that direction. What do we see? The very first thing we're going to see is a, what polarity, my friends?
Positive.
Positive. What value?
0.67.
Okay, so we have a positive 0.67 volts. We're going to add that to, then we go to here. Now from here, what do we see next? We see a positive. What value? 7. So we're going to add that to a plus 7. And then what do we see on the last leg going to ground? We see a what? Positive 0.33. So plus 0.33. So when you go to add these guys together, what will this add up to be?
8 volts.
What's that?
8 volts.
You have a polarity for me?
Oh, positive.
Yeah, so we have to call out the polarity, okay? So it is a positive 8.0 volts, yes? And because I kept these as decimals, it just makes the math a lot faster. Now, I have a question for you. This was point D, yes? Here's the red probe. And which way did we pull it towards the black probe? We came up and then over to the left, yes? Could we count the voltages going in this other direction? Could we count the voltages from D in this other direction going to ground? It should be the same if our numbers are right. Let's see if that works out to be true. Here's the red probe at point D. And instead of going up to the left, we are now going down to the left. So if the red probe is now here, and we're going down, what's the very first polarity it sees? Right there.
Negative.
It sees a negative. So voltage at D is equal to a negative, what value? 3 volts, yes? So we have a negative 3 volts. And then it reaches this point. Now, on the other side of the source, now we got to keep pulling towards the black probe. What's the very next thing it sees? What polarity?
Negative.
What value?
1.
So we're going to add that to a negative 1 volt. Now we've gone through this guy. Now we're at point F. Now we got to go up to ground. What's the next thing it sees?
Positive.
Positive how much?
12 volts.
12 volts. So we're going to add that to plus 12 volts. So we have a negative 3 volts, negative 1 volt, and we're going to add it to a positive 12 volts. So when we go to do the math here, my friends, what's that going to work out to be?
Plus 8.
Plus 8.0 volts also, yes? So have we proved to ourselves going around the circuit, doesn't matter which way you go around the circuit, as long as your polarities are marked correctly and your directions of arrows of the current are properly marked and the polarities of the voltages across the resistors are properly marked, it doesn't matter which way we count our voltages around the circuit, we should end up with the same numbers both ways. Are we good with this so far? We had 8 volts here and we had 8 volts here. Okay. Okay, I'm not going to go through all of these because I'm going to give you something interesting to think about. How about I'm looking for V, let's go F to C. I want VF to C. So instead of single points to ground, I now give you 2 points. How do I measure voltages between 2 specified letters? What do I do in terms of my schematic? What's going to happen with this? What do you think?
You would put your red probe on the F and black on the C.
Okay, my red probe should go to the first letter. So my red probe will come here. And my black probe will go to the second letter, which is C in this case, and it'll go over here. So here is point C. And now I want to read the voltages from the red going to the black. I've got 2 different ways I can do this. I can come up first and then over to the right. Or I can go to the right first and then come up. Which way do you want to go? Question goes to Harpreet. Question goes to Tony.
We'll go from the bottom side.
Okay, we'll go from the bottom. Yeah, okay, we'll go the bottom and then up. All right. So if that's our path, we're going to go along the bottom and then go up. The very first thing we encounter is a what?
Plus 1 volt.
Okay, so we have a plus 1 V. Now we're on the other side of this resistor. Then we encounter a what?
Volt.
A positive 3 volts.
3
So we're
volt.
going to add this to a positive 3 volts. Then we're now over to this side. What do we encounter?
Plus 0.67 volt.
Okay, so plus a positive 0.67 volts. So what do you total that up to be?
4.67 volt.
So positive or negative?
Positive.
Okay, yeah, you got to call it out. So positive 4.67 volts. Does anybody have any questions about how we determine 4.67 volts coming along the bottom and then going up? Anybody have any questions? Now, what we're going to do is We're going to try to reconcile VF to C going up and then to the right. We're going to take a different path. And so on this path, Andrew, are you here with us? Okay, Luis, if we go up
Yeah.
and to the right, what do we have?
First, we get a positive 12 volts
So we have a positive 12 volts. Then we're going to add that to a what?
to a negative 0.33 volts.
Negative 0.33 volts. And then we're going to add that to a what?
Negative 7 volts.
A negative 7 volts. So you have a positive 12 plus a negative 0.33 volts plus a negative 7 volts. So this works out to be positive 12 volts plus negative 7.33 volts. What is my net voltage here? It's going to be a positive 4.67 volts. Did we confirm this voltage going around the circuit in two different directions? Yep.
Yes.
And this is the concept that I want for you to understand about series opposing, series aiding, because these two are clearly aiding, opposed by the 12 volt source. And then that determines a total voltage, a net voltage of 2 volts on our VIR chart. So we have 2 volts net. 600 ohms calculates a current that is the same throughout the series circuit. Calculate the voltages. You write the values of the voltages right on the schematic. But the most critical part is, since this is the dominant voltage, counterclockwise is the dominant direction, and the dominant direction forces the electrons to flow in a clockwise direction, it dictates the polarity across the resistors. And the polarity across the resistors, guided by the current direction, mathematically allows you to solve for all of the voltages of interest between single points to ground and multiple points. Okay, that's the most important thing about this particular exercise.